Okay, we'll now look at the first interesting string matching method, apart from the brute force method that I would not consider interesting. And that's string matching with finite automata. And because this is a topic that's taught in most computer science undergrad courses I know, but not necessarily all of you have gone through one, I'd like to ask you about this. I should have said you can click you remember some of these even if you don't remember all of these, but maybe it's too late now. All done? Maybe not. Okay, 2/3 of you have not heard of these. The other ones, okay, this is how much you remember. All right. I don't know if it helps if I tell you that NFA are non-deterministic finite automata and DFAs are deterministic finite automata. The thing is, this is something you would do in a formal languages in automata class, but you might not have had one. It doesn't matter really. It will mostly affect you in the sense that there's some jokes in this that won't click for you. That's too bad. The point is, so this is part of theoretical computer science. The traditional theoretical computer science classes are one algorithms and data structures and one on formal languages automata. So you could say, if you've gone through this and you're one of the two lucky guys who clicked, I could still do this if you wake me up in the middle of the night, then the whole problem becomes very simple. String matching is a membership query for a specific language. Okay, for most of you this doesn't make a lot of sense, but I'll go through this and then you can forget about it because it's not relevant for the algorithms that we'll talk about. It's just a point of view. Finding a pattern in the text is the same as checking if the text has the form something followed by the pattern followed by something. Remember, sigma star is all finite strings, so that's something. This language is not an arbitrary language. It's a regular language, and that has a very formal meaning. In particular, it means there's a DFA for recognizing this, and, well, simulating a DFA on the text is linear time and checks. So that's almost the perfect algorithm you can have for string matching. So the theoretician might say, great, so this is solved. And the programmer might say, hold on. First of all, I might not have had such a course, so I don't know what you're talking about, membership queries, etc. But there's two actual problems with this premature drop done. One is, this is existence. That's not an algorithm. We also have to find this thing. And the second point is, this doesn't say how big this automaton is. So if we want to compute it, we have to at least write it down. And if that automaton is very, very big, the whole approach is fairly useless. We'll see that actually both problems are non-issues in this case. We can solve both of them. But they might justify a little closer look. But first of all, I want to tell you what a DFA is for those of you who haven't seen it or don't remember. A deterministic finite automaton for this class is essentially this picture, well, or pictures of this type. You have states, and you can be located in a certain state at a certain point in time. And then you read a new character that's fed to your automaton. And that character makes you go to a different state. by following the appropriate arc that's labeled with the character you see. And that means if you read a whole text, you will happily walk around in this directed graph, and you will always be at each point in time at a certain state. There's special states that are drawn with this double line. Those are called accepting states. If you happen to end in an accepting state when the whole input has fed into the automaton, then you accept. So DFAs are things that can accept or reject a certain input. That's all they can do. And we'll abuse the concept to find matches. We'll essentially stop scanning the text once we hit this accepting state, because then we know we've seen something followed by the pattern, and we don't actually care that there's more something to follow. Okay, let's briefly do the example. This is a specific automaton. It's actually one of the type that we'll need later. And there's a start state. That's this state number 0, where we are located in the beginning. Now we read the first character, which is an A. That takes us from state 0 to state 1. That's all it does. Then we read another A. That loops back to the same state, so we stay where we are. Then we read a B. That takes us from state 1 to state 2. Then we read an A. That takes us from state 2 to state 3. And I guess you can continue how this goes. It's very simple. A deterministic finite automaton has the additional rule that for every state and every symbol in the alphabet, there's exactly one arc telling you where to go next. So a DFA is the ones that are friendly for this type of simulation. There's always exactly one position where you have to go next. And if you keep doing this with this specific text, you will find that you end up in this accepting state. So there's an occurrence of the pattern here, but I haven't told you really how this DFA has anything to do with this pattern. But if you look at it, whenever you have seen this line of symbols here, it's obvious that let me start again, turn the sentence around. If you read characters starting from 0 that are exactly the pattern, you walk right into this accepting state and you're good. What's not so obvious is, what if you followed some of the other arcs and went a more crooked route? Why can you still guarantee that if you end up in this state, you will have seen the pattern? That's the magic behind this automaton, and you will understand soon how that works. Okay? But that's how a DFA works. That's how you simulate a DFA. You just go through the sequence of states and check whether you end up in an accepting one or not. Okay. This particular type of DFA is also called string matching automaton. It's a particular type of automaton that you can construct from the pattern, and a large part of this subsection will be about this. I want to give away the main insight here why this could possibly work. We will use the states to encode the following. If we're in state Q, that means in the text that we've fed into this automaton so far, that direction I guess, we've seen a certain prefix of the pattern. That might be empty, in which case we're in state 0. So pay attention that this is the exclusive syntax. So we've seen a prefix of the pattern up to excluding position Q. And we have not seen a longer prefix of P. That second part is also important. If we can guarantee that this meaning of the states is always fulfilled, if we end up in this state 7, that automatically means we've seen the pattern. And we've seen it just now. Okay? Okay, I have the loop here, so we might have seen it earlier. Depending on what, okay, maybe forget about this for now. So the easy part is, if this is true, this is essentially an invariant. if we can make sure we're in that state, if and only if that's true, say if I'm currently in state 3, so the longest prefix of the pattern I've seen is ABA. If I then see the next character in the pattern, the B, I know where I have to go. It must be state 4. If I don't see a B, I see something else, then I have to go to some other state. And that's where the trouble starts. But the interesting observation is, while we're actually feeding the whole text through this automaton, we don't have to remember the text. We only have to remember Q, how much of the pattern we've seen, plus maybe one more symbol that we're currently looking at. We can completely forget the rest of the text that came before. And that's because we insist that Q is the largest such Q. It's the longest prefix of P that we've seen. So one more time slowly. If we've seen a certain prefix of P, we read the next character C. Then we know that the text that we've seen ends with this. We also know that this is not a prefix of P, because otherwise it would be the other case, the easy case. And, well, this was the longest prefix of P that ended here. That means the new thing that can match, so maybe I should draw this picture. So this is our pattern up to Q. And then we see a C. So this is the text. And it continues to the left, but we completely forgot what this left part is. But now we read the C, and we know this is not the same as, it's not the same as the next symbol in the pattern. If we now want to find the new Q, that should be, again, the longest prefix of the pattern that we've seen so far, but it should match the C. Then this new prefix must be shorter than Q. It can be at most Q. The new state is at most the previous state. Just go through it. Assume it was longer, then the Q would have been longer too, and so you get a contradiction from that. Okay, so the magic why all this works with this deterministic automaton is you don't need to remember the text. You only need to remember how much of the pattern you've seen. And then with just looking at the next character, you can figure out what the new Q is. I don't expect you to understand how to find the new Q at this stage. We'll spend more time on this. Okay, back to the theory side. I asked the question not just about DFAs, but there's more theoretical constructs that you might not have heard of. The simple part, let's suppose we try to construct this automaton and start with a simple case. We can always write down this. We start with all the states in order, and we put in the symbols that we know. This is just the pattern, and if we find these in that order, that's our match. That's the easy part. The tough part is all those failure links, where all those arcs where you didn't find the next match. This thing, as it is, can be interpreted as a non-deterministic finite automaton, where any arc that's not there actually goes to an implicit dump state where you never get out of again. You can make this formal, but maybe since only a few of you have seen this, it's maybe not that insightful. You can also use this automaton directly to simulate reading the text. And in this case, you would maintain a whole set of states in which you could be in. It's a bit like quantum stuff, but it has some differences. Non-deterministic. It's not exactly quantum. You start in state 0. If you read an A, you can either stay in state 0 or you go to 1. That's what that means. And that goes on for some while. An interesting thing that happens here, if you read an A and you can be in state 0 or in state 3, the 3 is lost because you can't continue. The 3 is lost into a dump state that we don't list. So the only thing that's left is the 0, and you will always have the 0 in these states. This is another interesting one. If you look at this one, you currently have 0, 2, and now you read a B. You read an A. This is the next symbol. You read an A and you're in state 0 or state 2, then both move forward and you go to state 1 and 3. And this is a mistake. I should also have added the 0 because the 0 always stays. Okay, so you could in principle try to simulate directly the non-deterministic automaton, but because you have to maintain the whole set, this is not really a good approach. So then again, the theoretician says, you have an NFA and want a DFA. I know how to do that. There's an algorithm called the power set construction. That was the last thing I asked you about. Just apply that, maybe minimize the DFA, and you're done. Again, that's fine, but it's again a bit of an existential argument. There is, for any NFA, you can construct an equivalent DFA, and there's an algorithm for doing it. But the algorithm is essentially doing this. You create one state for every subset of states of the NFA. If you've never seen this, okay, I don't want to explain it. So there's a problem with that, in that you get many states potentially. Here we come finally back to algorithms and the insights there. So that's the first algorithm that we'll talk about, but it's also separately used for constructing the automata here. There's an ingenious insight that shows this exponential blow-up never happens for the type of automata that we build. And the insight is as follows, and that will be the last thing for today then. So try to follow this last thing. If we have an automaton built, so aj-1 is a partially built automaton of this kind I've shown you, but it assumes that our pattern stops at position j-1. So it's a smaller problem. You take a prefix of your pattern and you build an automaton for that. Let's magically suppose you have this automaton built for you. You can try to add the next character to this automaton and repair whatever's needed to get to the automaton for the one bigger prefix. There's one thing that's easy. You need another match state, so you attach a state j, and from state j-1 to state j, you will have the appropriate symbol. So you go and put this symbol. Hold on, this is one shifted. Now comes the, okay, I have to think. You construct this for the pattern here. So you want to put this on the edge. I guess that's the new state then. So that one's easy. But then we also need the possibility that you read any other symbol than that. And you have to add to j the new arcs that are now possible. So when you're in this state and you read something else than that, you would have to jump back. And we have to figure out where exactly we have to jump to. And the answer is, you can figure this out based on the same intuition we've had before, what the states should mean. A state Q means you have seen this longest prefix, etc., etc. So where should you go if you're in this state J and you read a C? You should go to, well, whatever's the length of the longest prefix of this, that's a suffix of this smaller one. And then append the C. I think there's the C missing. Let me double check this line. The insight is that wherever you go to, it will be further to the left. And that means you can use, to find that position you have to go to, you can use the automaton you already have constructed, the one for the shorter pattern. Tells you where you start, and then you just go one step from there. That's basically the solution. Let me double check the details here. I might have goofed at that stage. And I'll show you a detailed example how to do this next time. There's a very simple procedure to do it. Okay?